In the last session, we started to talk about momentum, and we said that a force is required to change the momentum of an object. So we said that the sum of the forces equals the change in the momentum per change in time. This was one way that we could define force, in this case as a change in momentum per change in time. When we originally introduced Newton's second law, we said that if you add up all the forces acting on an object, it equals the mass of the object times the acceleration of an object. Now these are two equally valid ways to talk about force or to define force. And in fact, we said that Newton originally defined his second law using the change of momentum per change in time. During this session, what I'd like to do is talk more specifically about why one form of these definitions of force might be easier to use in certain contexts than in other situations. So to motivate this, let's look at some acceleration versus time graphs. So to begin, let's make some acceleration versus time graphs. And then what we're going to do is we're going to use the acceleration versus time graph to make a force versus time graph from this graph. So our first case, let's assume that the acceleration is constant. And you should remember that if acceleration is constant, you'll have a nice straight acceleration curve. So in this case, our acceleration is constant. And what we want to do is use this idea to make a force versus time graph. And to do that, let's use some real numbers. Let's assume in this case we have a constant acceleration of 2 meters per second squared. Now before we go into making the force versus time graph, let's just take a look at what Newton's second law says. Now we've often been writing this as the sum of the forces equals mass times acceleration. And when the acceleration is constant, this is completely valid to say. But we have to keep in mind that really we can look at the force as the force changes over time, or the force as a function of time, which equals mass times acceleration as a function of time. Now in this case, we're going to just use this form because our acceleration is constant. And let's make one more assumption. Let's say that we have an object with a mass of 5 kilograms. And what we want to do is figure out what the force versus time graph would look like in this case. So what I would do is I'd use Newton's second law, and I would start inserting the values that I know. In this case, the mass is 5 kilograms, and the acceleration is a constant 2 meters per second squared. So in this case, since my acceleration is constant, my force will be constant. In this case, 5 kilograms times 2 meters per second would be a force of 10 newtons. So what that means, or what I should see, is that since this is constant, since my acceleration is constant, my force will also be constant in time. And what the mass term in this case does is function as a scalar to literally shift the force versus time graph up or down. In this case, it's always going to shift it up. So in this case, let's assume this is 5 newtons, 10 newtons, and let's say this is 15 newtons up here. Then my force versus time graph would also be a nice straight line because acceleration is constant, therefore the force equals a constant. Now let's compare this to an object that's not accelerating at a constant rate and see how we would go about figuring out the force versus time graph for that object. So again, I'm going to make an acceleration versus time graph. So acceleration on this axis, time on this axis, and then I'm going to use this information to make a force versus time graph. So let's assume that the acceleration is not constant. Let's assume that as time increases, my acceleration is going to increase. So I'm going to not just be moving at a constant acceleration, my acceleration is continuously increasing. So let's look at, say, 1 second, 2 seconds, and 3 seconds. And let's say I want to know what the force is at this point here. Well, the first thing I'd have to tell you is what's the acceleration at that point. And let's assume that the acceleration starts at 0. So the acceleration starts at 0 meters per second, and it increases until it hits an acceleration of, say, 2 meters per second squared. So the acceleration is continuously changing. And let's look at what Newton's second law says for that one. So in this case, we'd say that the sum of the forces as they vary over time, or as a function of time, equals mass times acceleration as a function of time. notice that acceleration changes in time, and so the force will change in time. Let's assume that our mass stays at 5 kilograms, so we can make a comparison with the last graph that we made. All right, so now what I'm going to do is I'm going to look at the acceleration at time t equals, say in the first case, we'll look at the acceleration when time is 0, or at 0 seconds. And in this case, I can go right back up to my graph, and I see when t equals 0, my acceleration will equal 0. In this case, 0 meters per second squared. So if I wanted to figure out my force, or the sum of the forces when time is 0, I plug in that point, and I write mass times my acceleration at 0 seconds. Now in this case, this will be 5 kilograms, because that's a constant, times the acceleration, which I figured out by the graph, is 0 meters per second squared. And in this case, my force will be 0 newtons. So I would go over to my force as a function of time graph and just put that point there. So if this is, say, 0 newtons, and this is 0 seconds, and then 1 second, 2 seconds, 3 seconds, and I want to figure out what my force is at the point where t equals 3 seconds. So to do that, when t equals 3 seconds, so my acceleration at 3 seconds in, I would go back over to my acceleration versus time graph, and I'd go 1, 2, 3, and up, and then I'd go over to my acceleration axis, and I'd figure out that when my time is 3 seconds, my acceleration is 2 meters per second squared. So I'd go back down and say at this point, this would be 2 meters per second squared. And to figure out my point where, or the point when my force is 3 seconds in, then it would be mass times acceleration at t equals 3 seconds. And in this case, this would be 5 kilograms times an acceleration of 2 meters per second at that time, or 2 meters per second squared, excuse me. And in this case, this will work out to be 10 newtons. So I'd go back up to my force versus time graph, and if this was, say, 5 newtons, 10 newtons, and if I kept on going, I could figure that out. And then I'd go over to where t equals 3 seconds, and I'd plot a point. And my graph, or my function, my force versus time graph, would be a nice linear relationship. So in both cases, notice that when I multiply by my mass term, all it does is it scales the acceleration versus time graph. Mass in this case is a scalar because it remains constant. So to make any graph from an acceleration versus time graph, it's really just a scalar multiple of your acceleration versus time graph. Now notice in both of these examples, I used relatively simple acceleration versus time functions. In the first case, it was a constant acceleration. In this case, it's a nice linear relationship. But what would happen if I had some bizarre looking acceleration and I didn't know I didn't know the relationship between acceleration and time? So let's, as an example, so if this is my acceleration versus time graph, and I had some bizarre acceleration that looked maybe something like this. So at first the acceleration increases to a maximum point, and then begins to decrease. What would the force versus time graph for that look like? Well, as you should see, all it would be is a scalar multiple of the acceleration versus time curve. So maybe it would look something like this, where the force increases until a maximum point and then back downward, where it hits some maximum value. Now, if I knew the exact shape of this curve, then I could figure out the force at each point in time. So if I knew the exact shape of this curve, and here's, say, 1 second, and maybe this point is 2 seconds and 3 seconds, I could go up to my curve and then over and figure out what the acceleration is at that point. And then I could do the same thing over on my force versus time graph. I could go up and over and figure out what the force is at that point. But oftentimes, the acceleration versus time graphs can become so complicated and difficult to analyze, we can't do this simple manipulation where we look at the curve and figure out what the acceleration is or what the force is. So this is where Newton's second law becomes very powerful. And what we're going to do is, in the next session, we're going to look at how Newton came up with a way to overcome this problem.